The plan here is that I will give first I'll give like a very quick introduction to the software. Um, then I'll kind of follow the user's menu and then try to really show how we can set up this sort of install this code and get the code compiled. Then show you how to run the calculation. Then we'll discuss the input files that you need, right? Um, I guess, as I said, I'll actually show you some sample input file, some sample output file. And then hopefully towards the end, I'll let it talk to discuss a little bit about the post-processing sort of procedures. Okay. That's really like how you actually how you're going to make a plot, like using GMT or various software, right? So that's sort of the plan. I guess like the idea is, as we sort of said before, is we kind of hope the first this tutorial will last about uh, somewhere between 1 and 1.5 hour today. Okay. Um, so, and also feel free to stop me any time. Okay, right. So now let me actually quickly sort of discuss a little bit about the history of this software. Okay, and so here is like a quick PowerPoint that I prepared for this. So this SICOM SVE is a parallel fine element software that actually to model elastic and viscoelastic deformation on regional and global scales. And so here we're actually going to mostly focus on the global scale. Um, and this of course is really for looting problems. So you can use this software to compute like surface load, such as GIA problems, and also tidal nodes. Okay, right. So this code actually will really build out of this thermal convection code called CitcomS, which is of course for viscous fluid, right? And then the first version of this is CitcomSVE for viscoelastic deformation is really initially for incompressible mantle, was developed in 2003 with my former student Archie Paulson and also my former colleague John Ward. Okay, and then Archie Paulson for his thesis work, he actually incorporated this degree one motion and also polar wander and the sea level equations. And the mantle compressibility was later on added by Guru A. That's in 2013. Then in the last few years, we actually worked on this code continuously to upgrade. The most significant feature of a few years ago, we upgraded this code such that it actually can handle more than 1,000 CPUs. And that is actually a big upgrade from originally it was only for 12 CPUs. And also the new sea-level equation and the mantle compressibility, then this is actually added to this new version, CitcomSVE 3.0. That's by Tall, and this is actually this paper 2025 benchmark paper. Okay, so that's sort of a bit of a quick history of this. And this is a slide showing basically the grids, finite element grids. And so what do we actually do here in this code, in this software is really you take a spherical shell, right? You first divide the spherical shell into 12 roughly equal size blocks. We call it spherical caps. There are 12 of them. And so this is a three-dimensional view. Let me see if I can. Um, so yeah, so this is three-dimensional view, how we actually divide the spherical shell into 12 caps. And then this is a map view, and this is how we numbered, right? And this actually is really the element we're using. This is element that we call the trilinear elements, and that is we use 8 nodes per element. Okay, and then the reason we do this division, of course, is really for parallel computing purpose. Okay, right now you can imagine each block can be assigned to a CPU. And then, of course, you can also imagine that you can further divide each block into, say, sort of more blocks, then you can assign to, more CPUs, right? And also I would like to point out that this kind of grids actually avoid this potential issue with this regular kind of grids in spherical geometry that often give you the excess resolution near the poles, right? So, but I guess these elements design kind of avoided that issue. Okay.
So,
And
CG, just to make sure,
yeah, yes. Hello?
sorry, um, I just got cut off again. So we should always use a multiple of 12 for the core number, even though you're
Exactly. So
using,
we're going to get it there.
okay,
Yes. And
okay,
yeah, the total number of CPUs will have to be multiple of 12.
okay.
Yeah. That's, yeah. And so I just want to quickly show this is actually really in the TOS, 2025 paper. And I just want to show you the kind of in terms of GIA problems, the kind of accuracy, the kind of CPU times that you may sort of expect. This is actually just, a calculation for a typical GIA run that is with I6G ICE model and the VM5A, yeah, VM5A viscosity model, right? And so you kind of sort of see the first column here, the right, and the left-hand column basically showing the radial displacement at present day time, and this is actually the eastward motion. This is all the rays, and then the bottom one is really for the geode rays. Okay, and then on the right, actually, will be the difference from the semi-analytic solutions, and you sort of see the scale bars are different. So, and so this kind of tells you what we can do. Of course, you run this calculation for one glacial cycle to present day. The results here showing are for present day. Okay, right. And this is actually showing the cumulative radial displacement at different wavelengths, different spherical harmonics, and at different, versus time. Okay. And so I just want to show you the horizontal axis here is the time, right? The vertical axis is the displacement. This is at a different wavelengths. For example, this is degree 1, degree 2, and this is a degree 5, degree 9, and etc. Okay. Then here is showing you with three different resolutions. Okay. And so the resolution R1, R2, R3, then the dashed line is analytic solutions. Okay. And so I guess this is, I should say there's L equal to 1. That's actually really the so-called apparent motion of central mass, right? So that's L1, L equal to 1 term. As you can see, of course, long wavelengths, you couldn't really see any difference among these different resolutions and the analytical solutions. They overlap, onto each other, right? But if you go to shorter wavelengths, like L equal to 23, this is the spherical harmonic 23, right? Now you start to see the difference between the analytic solution, right, the dashed line, and the other three numerical solutions of a different resolution. And R3 is the highest resolution in this calculation. Okay. And I also want to quickly point out that the panel D here is really for the degree 2 and order 1. This is really the measure of polar wonder. It turns out that actually polar wonder requires more resolution. Okay. That is, you sort of see the, even the really long wavelengths, but somehow, is really more resolution demanding. Okay. Quickly, this is actually one table from TOS paper. I just want to kind of show you this three different resolutions, right? This is the 48 by 48 by 48. This is actually for one of the 12 spherical blocks, number of elements we have, okay, right? And then this is 48 by 80 by 80. So the 48 here is really in the radial direction, the number of elements. And 80 by 80, those are actually in two horizontal dimensions, right? And R3 has got the highest resolution, okay? Now this is the total time step we use for this one glacial cycle. Right. And so this is really depending on what the time increment you want, right, for your calculations. And then this column or this row, so saying the number of CPU cores. So we mostly use this 96, right, for R1, R2 resolution. For this high resolution R3, we actually use 384 cores. Then this is the clock time, runtime, right? And this is in hours. So, this is, basically, we can get down to something like 5 hours if we use 96 cores on this kind of resolution. Um, Actually, I think, sometimes actually I got even 3 hours, for this R2 resolution. Okay. Um, so
Why
then,
why is R2 faster than R1?
let's see. There is this tall. Let's see. What do you
Yeah,
think?
R1, I think R1 is because for this kind of resolution, the element is not in a good kind of size, so the convergence is not
Oh,
very
okay.
fast. Yeah.
Yeah. Sometimes the high resolution helps the convergence. This is so that's but I guess roughly this is sort of the expected CPU times that you may need. Okay. Then this is the sort of the core hours. That's really the number of CPU hours multiplying with the number of cores. So that's essentially what we're talking about. So this is actually give you a way to estimate like uh, how many, if you, depending on the number of CPU you use, like, what would be the typical, wall clock hours, you may expect. Okay, right. By the way, I should say that this 80 by 80, right, for one of the 12, each of one, for each of the 12 blocks. And this will give you about 80 km resolution horizontally. Okay, not great, but that's kind of the, right. Some of our calculations, we actually got to resolution of, 50, 30 kilometers horizontal resolution. Okay, right. There's also this capability to do grid refinement, like some of our calculation for Antarctic. Donna, actually, right, she could get down to something like a 10 km horizontal resolution for calculation for Antarctic there. Okay, and there we actually can do grid refinement. But anyway, this is sort of the accuracy that in terms of percentage of errors. So if you get to something like R3 resolution, we're talking about the radial and the horizontal and the geode rays. So they're kind of we can get down to like a sub 5%. This is comparing with analytic solutions, right? So then the relative sea level can get even, this is bottom two rows are actually for relative sea level accuracy. Okay. So anyway, this is just kind of overall about this capability of this software. Okay, right? So um, yeah, let's see. Do we have questions about this? So as I said, if you are interested in these numbers and the benchmark and the TOS 2025 paper, really is benchmark paper. So kind of really, you can sort of get some ideas from there. Okay.
Hey,
Uh,
Shiji, we have a question in the chat.
oh, okay. So, um, okay. Oh, the core. Yes, of course. I should have said that we actually use all the numbers that I called here actually for NCAR, this NCAR supercomputer called Duratia. Actually, I'll show you that computer. I think that computer sort of uses the AMD, Milan kind of chips. So yeah, I mean, if you, of course, if you have different, you use different CPUs, different, right, chips, and then the CPU time will be different, of course. Yeah. Okay. Yeah. Okay. So, um, yeah, let's see. Now so this is users menu, got quite a lot of stuff we covered here. And I'll actually quickly go through, to, let's go to the installation, right? And this is installation of this software. I don't know how many of you have tried this. I actually download the package from GitHub, right? That I emailed you that GitHub link. And so now let's just so this is here. This is actually the computer that I've been using today for the demo, right? And this is the Durasia's NCAR's NCAR's supercomputer. So if you actually see, can you actually see the my screen here? Can you?
Yes.
Yes.
So this tar file, this is the one that I downloaded yesterday, I believe, or the day before yesterday somehow. Yeah, and actually it's a couple of days ago. Okay, and so now I'm going to kind of basically unpack that, right? So so use tar. I guess here is this particular option. So right, I'll just kind of now I got this directory. Okay, right. This is a blue color that's really unpacked. So I'll go there, right? So this is essentially is what what I have. Okay, and then you still have a few more tar files here. That's we could actually have put everything into one tar file, but the GitHub got this 25 megabytes profile kind of limit. So I had to break this into basically three different tar files. So and then I guess we can just unpack. So this is the one that according to the user's menu. This is the one that we have to unpack next. So now if you see now this is the one. So this is CitcomSVE dash 3.0. That is really the directory that we're most concerned. Okay, and so so let's actually go here, right? And the first thing that we actually said in the users menu here, right? So we go to this directory CitcomSVE, sort of 3.0. Then we do this config, and this is basically try to build the kind of search the computer system, right? And that you use them and really try to kind of find out the system information, then create various make files. Okay, so this is this actually run very quickly through this our system, right? And so and I guess yesterday I sent out an email. I try to simplify this process. That is to skip the config step. It is actually possible to do that. And so I emailed you yesterday. I give you a single makefile. If you want to follow that, actually very, very simple. You can avoid this configure step, and you can, you produce the executable that just work equally well. Okay, right? So anyway, so we just we just config. Now this is create various make files, and now the next step is to compile. So you just kind of type make, right? And so this actually will produce executable, right? It's called CitcomSVE-3.0. And so now you may see some warning. It's not really a problem. I should also say this code was built out of convection code. There are quite some subroutines that are not really useful for GIA or for viscoelastic problems. Okay, right? So yeah, so it's probably take a few seconds and we'll be done. I think we're almost there. Yeah, so it's done. And so now we compile the code. So if you kind of read the user's menu, now the executable is called the Sitcom S4. It's in this directory bin, the Sitcom, SVE 3.0 bin. Now if you go here, right, and you see there is this bin here, right? So we can, sort of see, right? Now this is a Sitcom S4, the in green. Those are actually the executable that we can use. There's also this Sitcom S regional. I don't think we actually fully developed that yet, at least for the viscoelastic problems. Okay. But anyway, so this is what be the executable that we can use. And so you also see here there are some, few .c, files in this bin directory. And, all the source code, they're either in the bin directory or there is another lib, okay, right? And so there are most of the files are actually here in lib, okay? And this is .c. As I said, many of these .c codes, they're for convection, some of them really for convection, not really useful for the loading problems we have here, okay? And so, as I said, I guess I probably should also mention that really a firm believer in open source. The convection code, CitcomS, was the first open source code in mental dynamics that was actually made available to general scientific community about 20 years ago. Okay, right? And so we're basically doing exactly the same thing. And as I said, I'm a firm believer in open source code. So this actually we got a license for this open source. This is really the least restrictive license that you can have these days. And so pretty much feel free to do anything with this code, right? So anyway, so given that, now, so we now here there are there are actually two other tar files. One is actually for I6G, so we needed to put those two tar files in the right place. So let's, so I'll actually go back. So this is where right. So there's I6G. This is really just tar file for our I6G, and I'm going to put this in, as said in the user's menu, right? So actually, I'm going to put that into here. Okay. So then I will go to the data directory. Now I'm going to kind of, untar this. So it's XZF. Right. So now I have this I6G 1 by 1. That's really 1 degree, 1 degree by 1 degree. This is for I6G. This is Dick Pautier's I6G ICE model, right? And so I believe this one only got the 26 for last 26,000 years, right? And so now there is, this is a cookbook, of course, this is for comparison. This is really showing the examples. This is the other one, okay? And so, yeah, we can certainly do that as well. But let's see. Now, so I guess at this time now, we're pretty much ready to run some calculations, okay? Because we got everything here already in this directory, in this data directory. Okay, so let me see. So in this user's menu, the way we present how to run this calculation is really assume you have some kind of PC cluster that we used to have. We still have a PC cluster in our group, but for the last few years, we're basically move everything the calculation to the NCAR's supercomputer. But this example showing still using MPI run for PC clusters. Okay, right. But the basic idea is quite similar. Okay. So I'm not going to really go through how to run the calculation using the PC cluster. I think this is really the explanation here in user's menu is rather clear. And rather so I will actually show you how I would actually do using the NCAR's supercomputer. Okay, so let me. Um, so let's see. There is this. Give me a second, and um, so I have. So with NCARs, the most supercomputer centers, you have to submit, like a queue, right? And so submit your jobs, through the queue system. So I have here is this, it's actually is this job file, and so I will just copy this job file over, and so then if I open this job file, and I just sort of you actually mm, um, so this is basically at least for this one, you have to specify how many CPUs you use or core. Like here, we actually use in this case we use 96, right? And so then I let's see. Yeah, this is actually this was for one particular round. So I'm yeah, kind of getting the tutorial. So this is I'm trying to find the correct directory, right? So for this executable, okay, right? Now this is the executable that we're talking about, Siccon, right, in Bing. So this is really right, Siccon SVE 3.0 Bing Siccon S full, right? So you need to specify when you run your job, you need to specify the number of CPU cores you need. Then you also have to give the input file. Okay, this input file is giving here. This input file 6G VM5A 1. So it's actually and so at least when you run this calculation, you will have to kind of this is how you actually would run. And different machine will have a different way of running the calculations, right? But this would actually be how I would do it, right? So now if in our case, I would do this Q sub.
CG,
Yes.
just it might help everybody if you could actually paste that file into the chat so people could actually get a text copy and then work with it.
Oh, okay. So let me see. So. Um, let's see. How can I?
You just open up the chat and just
Yeah.
paste it
Okay.
right in there.
Here it is. Yeah. Yeah. Okay. Got it. Yeah. Good. Um, so, um, so now in my case, I'll just kind of, right. This is how we submitted this job. So it got job number here. This calculation will take about, I'll say, it will take about 3 hours to complete. Okay, I use 96 CPUs. So let me see what is the status of this. So. So it is running now, sort of it's running. I so let me see what actually we said here. So here, as I said, of course we need the input files, right? So in that, there one input file we already see that's this guy, right? It's in this. MPI run kind of, right? We kind of directly call this input file. Okay, so this is one input file that we need. Then of course you can imagine you would need the input file for your Earth model, with Earth viscoelastic model, right? And you also need input file for ice model, right? To run a GI calculation, right? You need the load, you need the Earth structure. So we'll kind of get to there. Okay. But anyway, and this is actually, if this is just really we start doing the calculation. And so I just want to quickly, so I know there is this, right? So this is where the files, the output files are. So in this BM, the benchmark I6G, right? So and there's this log file that is very important, very useful. That really tells you the progress, what's going on. So there are a lot of, so for example, at the moment we're actually at time step 10 already. Okay, so this is time step 10 already. And so it's running very quickly, right? And so and you can find a lot of information in this log file, okay, right? And so now I think I probably can, so we don't want to waste CPU time. And so I'll go here. Maybe I'll just, Yeah, it's already. So this is where the output is. Okay. That you can specify, of course. We actually specified this. I'll discuss that very quickly, right? And so now I can sort of see all the different files that the user's menu really explain all the output files, right? And there are quite a bit of message here I use. Okay, different. Yeah. Okay. So yeah, actually, yeah. So. Yeah, okay, that's fine. Yeah, that's good. So yeah, so let me just try to see if I can. So here, if I want to delete this, and this is what I do, and I'll just Q delete, right? And then I'll just take the job number. Sometimes may need to take a few kills, and so anyway, now so so that's really how you run this calculation, at least on my computer, right? And now let's look at the input file. So this is actually user's menu, right? So this is the input file that I used for the test run. So this actually is all under the directory data, right? And so if we kind of just open up this 6G VM5A1. So this is one that that I used. So you sort of see, remember I actually mentioned to you the output files is under this data directory, but then is in this directory called the BM benchmark I6G, right? That's where the output, was, right? So, um, so let's see, and I'll just kind of go there, tutorial, right? So, right. So now here, so this is where this is the directory, right? For benchmark I6G, that's where the output files, this is here, okay, right? And so then the case one is actually for the output file, we can have a given name for each case, right? So we use case one there, then all the file names actually will in this directory will for this calculation will start with the case, file name will start with the case one, right? And then you have like topography, stress, whatever you want, right? And so now let's see and so in this input file, there are, basically 5 different groups of sort of parameters or input you need, right? And some are actually not, some are not as important, so this really here, in this user's menu really explained line by line everything. Okay, so for example, group one, general information, right? That's right. You can sort of see that's group one, general information, what they are. I kind of already explained this. Now the next parameter is the compressible. So this code actually the 3.0 version, got this switch. You can do compressible, like so. If you turn this compressible to be one, so then you were doing compressible calculation, fully compressible, okay? Right, this is really I guess our papers describe the mathematical formulation. So this is like fully compressible. But if you turn this to 0, then basically you're running incompressible model, okay? Right, then after that is the sea level. Whether or not you want to apply the sea level equation, one means yes, we applied, sea level equation because we're running GIA problems, right? You can imagine some people actually use this code to do the lunar tidal deformation calculation. There's no ocean there, so right, no sea level equations, right? And then there's polar wander, so if you want to turn on, most of the time, of course, we turn on the polar wander because that's important part of the physics, and right, and so you turn on the polar wander. Then there's also this polar wander. This is fluid lava number, okay, and that is you have to kind of apply, really give the fluid lava number, which depends on, as some of you probably know, it really depends on your Earth's structure, right, density, etc. And then you have information like how frequently you want to output your results. Like here, storage space in surface. It's like your surface topography, gravity, and how many time step you you run the calculation, then you want to output, right? So it's like here's every 10 time step, we output the surface information. Then sometimes we also ask you whether or not you're interested in volume. That is, if you're interested in stress field, viscosity in your three-dimensional Earth mantle, right? And now you can imagine, a lot of times you don't want that because really to store this is very expensive, right? You need a lot of disk space. But there is an option to do that. So in this case, you can also specify how frequently you want to output this, right? And then after that, I think I tried, this is actually users menu follow this input, this input file very closely. So you see there are a lot of explanations, right? Now we actually get to the LL max and those, so 32 harmonic. So this is L max. This is really the number of spherical harmonic degrees that we use. In calculating the gravity field, okay? And so, although the equation for motion is solved using finite net method on this finite grids, but the Poisson's equation, which is the calculation of gravity field, at the moment, we're still using this spectrum method, which so in this case we only use 32 harmonics up to degree and order 32. Okay, so this is where you sort of can specify. I guess we in our own experience, I guess the largest number that we used here for this max LL max is probably about 64. And so actually this can get very expensive and the calculation of a spherical harmonic solutions of Poisson's equation. Okay, so beware of that. Don't use 500. Okay, no, really. So anyway, now so here it became kind of important. There's this one parameter called the heavy side. Okay, now you can sort of see, this switch really tells you about now we're actually getting to group 2. Of the input parameters, right? So the heavy side is an important parameter for all the ice model calculations. We actually would turn this to be heavy side equal to 2. Now, if heavy side equal to 1, that's really for step function in time loading, right? So if you have if you switch to this to 1, then you basically have a step function, loading. And there's also possibility of using heavy side equal to 3, that actually give you sinusoidal loading with time, okay? But for most of our GIA calculations, because ice model got all this weird time dependency, so we always use heavy side equal to 2, okay? Right? And then, after that, then you have whether or not you apply the potential, right? And so 0 means you use the surface load for ice models, or for sometimes volcanic loading, and those are actually all the surface load, right? So that we use 0. But sometimes if you want to do like a tidal calculations for the moon, as I said, or for the Earth tidal deformation, then you may actually switch this to 1. Then you have to specify what really what kind of tidal potential you applied. Okay, so that's really hot for the we're talking about this applied potential aspect, right? And then.
CJ, can I just
Yeah.
keep going? Maybe slow you down a wee bit. I'm still confused between heavy side and ice model. Like ice models are usually applied as heavy side functions anyway. Like, are these like
yeah. So the heavy side, when we at least the way we define here, the real heavy side function is a step function in time, right? And so whereas the ice model, you kind of, like I6G from Dick Pautier, he one, right, got a 49 stages, right? So that we call that just really ice model. So I would just say we use 2, for this parameter for all the ice models calculations. And so you design that into, basically different stages of loading. Okay, so we always use 2 here. So if you have other, yeah,
what's the kind of the default time step for the calculations?
We'll get there. Okay, yeah,
Okay,
yeah, and so, but anyway, then there are and this is basically if you use a single harmonic loading, right? That is true if heavy side equal to 1 or 3. And so often in that case, we often do single harmonic. So this is where you actually provide the information like degree two, L equal to two, M equal to zero, single harmonic loading, right? Very good for benchmark, code. So anyway, and so there's that. And then now this next, here now is really the question that, Nev actually kind of asked earlier. That is, now this is loading stage. So this is, you can sort of see the ICE 6G26, KA. So that actually is really in this data directory, and there is a file. Basically is what we call the, sort of time stage file, right? So I don't want to get to a lot of the details here, but this is essentially what is this file looks like. And we actually, I think in this we discussed about that already. Somewhere there is a discussion about these files. For example, section 4.3.1 really describe this particular file, and this is where you actually can specify the time, the delta t. Okay, right? How you want delta t to be 100 years or 300 years, whatever, right? And so this is actually all, you kind of quickly see, for example, the 49 means there are 49 stages, and then each nine really tells you about what's the situation for each of the 49 stages. And so the first number, for example, 12022, you probably realize that's 122,000 years right ago. And this 180 means the number of time step for that first stage, which is really from 122,000 years ago to 104,000 years ago. Okay. So anyway, and this is, as I said, we will not have time to discuss the details like this here today, but this is where, if you're curious about how many for your ICE model, how many stages you have, right? Loading stages. For each loading stage, what is the time from, right? Beginning time, ending time for each stage, then the number of time step you use, for that stage, and that's all here in this file. Okay, so
And are you interpolating
yes, in between
the
linearly,
input
yes,
slices in between those two stages?
yes, linearly,
Okay.
yeah, linearly, yeah. So your load, so that's actually here now. So now you can see. Now we start to talk about the ICE models now. The actual. So
世界. So
yeah.
why you have 26Ka in the name of this file?
Yeah, that's because the I6G, there's this one particular DeepPower-TS I6G, it really describes the deglaciation, really since the last glacial maxima. Okay, so, but it's really, the calculation is really for full glacial cycle, right? It's 122,000 years.
Okay, I see.
But the DeepPower-TS model only, at least the model we're using for this example case, really kind of start at 26,000 years ago. Okay.
I see. Okay.
Yeah, that's just file name. So this file name, you can name anything you want, right? And now we actually get it to the I6G files, okay? And so I guess here we're just using the I6G. This is actually on degree by degree. And you remember I actually sort of copied this over, right? So if you go to this I6G, this is essentially where all the ice model and ocean function we have, okay? So there are 49 of them, or maybe 50, because it start from 0, right? This is I6G dot 0, dot 1, then all the way to dot 49, okay, right? So this is actually, those are ice models. They're on degree by degree. Then there's ocean function, for each ice model, right? And you have ocean function with it, right? So this is actually all given here now, okay, right? And so that actually specified in here, okay? So the I6G, and then this is, right, this is ocean function 6G, and this is like the prefix for those files, right? Again, those this is I6G files. They explain, they're actually explained their format, and they're actually explained in, in this user menu very carefully. I think, for example, the section 4.3.2, that kind of really describe how to build the ICE this your ice model. You can have your own ice model, but as long as you follow this format, then everything should be fine. Okay, right? And so that actually,
What about,
yeah.
so do you have code for generating the ocean functions, or we have to use our own code for that?
Yes, and hopefully Tall will have time to kind of, yeah, there is a file called pre and post. Let me see if I can. So um, yeah, so there's a tar file here, the pre-post processing. And this really is doing all the pre-processing that generate the ocean functions and based on your ice models and based on bathymetry, right? Then there are also post-processing. So there's actually users manual also discussed about how to use this package. Okay, we'll see if talk will have time at the end to kind of maybe give a few minutes, introduction to the pre and the post processing. So we'll see about that. And so now let's see. So at this point now, we basically talked about the group one input and group two, right, in this file input file. And the group two is for load, right? And so so that's that's what we're so this is group two is really for load, right? Now the next thing, of course, would be let's see, this actually will be group three. Now you run GI models, right? You need you need a load, that's I6G, which is discussed. Now the next thing, of course, will be the Earth model, right? Or the material property, Earth viscosity, elasticity, density, etc. Right? So this is actually now the group three really for that. And so now you the most so here there's this 1D model data file. It's called model prem. So you can sort of see and VM5A, right? With this is actually with cross or without cross. But anyway, so I can quickly show you. There is the file is already here. That's this one, right? So model prem. So now this is really what this file would look like, right? And sort of really this is mostly prem, okay, right, for the Earth mantle. Then except there is viscosity here, right? There is also it's last column some kind of material group numbers. But anyway, this file really described the Earth model, right? And I think actually we sort of said this is VM5A, so therefore this column, viscosity column, you can sort of probably can recognize this is Dick-Paultiers, VM5A, right? This is versus radius. Okay, the first column is radius. This is all kind of giving in here the VP, density VPVS, right, and little g, and right, and so then there is also a possibility. This is just another. There's a possibility to read read in the little g as a function of radius. Okay, that's an option here. But for now it's zero, meaning that we just calculate little g gravitational acceleration based on the density provided in the file. Okay, so then if you want to use a 3D viscosity, many of you probably would like to do that, right? So in that case, you have to turn this parameter like from 3D viscosity from file, you have to sort of turn that into one. Like currently it is zero, so that's because we use VM5A, right? So this is actually so now if you use a 3D viscosity, then you have to provide what the 3D viscosity you have. So this is really that, and this give you this file really provided a 3D viscosity. Again, this user's manual describe how you prepare for this 3D viscosity, right? And so you can sort of see here, right? We actually there's a tells you like a section section 2.4.2 really discuss how you would prepare for this 3D viscosity file. Okay, right? And in this users in this data directory. We have that file. If you want to kind of take a quick look, that is. So this is that file. Okay, it's right. This is really that file. And really it's rather self. If you open up, you actually will see sort of with a lot of explanations already in the file. Then the user's menu, of course, explain a bit more on this, right? And so that actually is a viscosity. Now you can also imagine that potentially you want to use a 3D elastic structure, say from tomography. If you want to take a tomography model, right? And that's a 3D, elastic structure. And so now at the moment is this zero, so for 1D plane model, right? And but if you want to try some 3D elastic, file, then you can also do that, just like how you would do for 3D viscosity. Okay, and so at that point, I guess by this point we already kind of more or less get the viscoelastic structure right into kind of discuss that already. And so
So sorry, CJ, but
yeah.
Under the same directory of VE.
Yeah, we don't have elastic. Yes, we only have viscosity files. Yeah, we can.
Okay.
Yeah, that's true. So if you want, you really have to build your own elastic file. That's exactly right. Yeah.
Can I,
Yeah, so and there are a few other things here. It's really kind of set the maximum viscosity, minimum viscosity in the calculations. And this is actually, I should say, this is a non-dimensional viscosity. And so I'll right, it's normalized viscosity. So this is why you see 10 to minus 3, 10 to 5, the maximum, right? And so it's not in Pascal second. But actually, you discussed about this, how to normalize in the user's menu. Then there's also possibility to do stress-dependent viscosity. So at the moment, okay, actually turn off the stress-dependent, right? So, but if you want to turn this on, then you actually can run calculations with non-Newtonian rheology. So then you have, basically various exponent, in terms of stress-dependent viscosities. And transition stress, etc. Okay, so I'm not I go. So then there's also this is when you do non-Newtonian,
May I?
calculations. Yes.
Thank you. Sorry. Maybe this is a bit specific. I remember in Tao's paper, there was like an applied viscosity that was lower on plate margins. And I was wondering, is this made through the viscosity file or through the like stress-dependent viscosity section?
Yeah, so that's a good question. That actually is through, in Tao's, recent paper with weak plate margins. Those are actually done through 3D viscosities, not a stress-dependent viscosity, just 3D. And so it's really just weak zones.
Thank
Okay.
you.
Yeah. Okay. Good. Yeah. And so yeah, those yeah. And so, but if you want, there is this capability of doing stress-dependent viscosity. One of my former student, Kai Xuan, Kang, we actually published a paper in 2022 that uses composite rheology. That is a stress-dependent viscosity. Okay, so now of course there's parameters like what would be iteration tolerance level for doing stress-dependent viscosity, etc. Right? So I guess at this point we talked about the ice model. We talked about the Earth model already, right? How to, in general, how to, kind of input those. Now, the next thing, of course, is really the model domains. So that is how many number of, right, the number of elements you use, right? So the number of CPUs or cores, and so that's actually the group of 4. I believe this would be the last group of parameters we're going to discuss today. And because group 5, basically, you don't need to touch, almost never need to touch group 5 parameters. So now the group 4 here. So earlier we talked about the number of this is actually this just is a parameter, so the 12. Okay, so this is really, and this number will almost never change. Okay, because that's 12 blocks we divide the Earth's mantle to, right? And so then within each cap, within each spherical cap, there are 12 of them, right? And then we actually can further divide into smaller blocks for parallel computing, okay? And so, which means that you can do that for the Z directions, that will be in the radial direction. In this case, we actually further divide into two, okay? And then we can also do in two horizontal directions, right? So I'm not saying longitudinal or latitudinal, longitude direction, because they're not, the caps, they're not really follow the longitude lines or latitude lines, right? So they're in horizontal directions, so X, Y. So in this case, basically, where we take each of the 12 spherical caps, then we divide in, basically into 8, right, 2 by 2 by 2, 8 smaller chunks, okay? And now, so basically it means that we would have a total of 8 multiplying with 12, which is 96, small blocks. Then each small block will be assigned to a CPU or core for calculations, right? So that's essentially what you actually see here, okay? Now, the next three numbers, they're showing you for each cap, right? There are 12 of them. For each cap, the number of nodes in I guess first X, Y, those are two horizontal directions, right? And then you actually have and Z, that's in the radial direction. So we have in this case, so maybe if I can, get to users menu, go all the way back to here, right? And so this is we're talking about, in each of this block here, right? And the total number of nodes, right, in three directions. So X, Y would be in two horizontal directions, right? And then Z actually is in the radial direction, okay? And so we have 81 nodes, right, in each of the horizontal, directions, and the 49 in this example case in radial directions, right? And the number of elements is always one less than the number of nodes, okay? So we would have 48 elements in radial directions. Now this is here is kind of get a little bit of complicated. This is actually we're using multi-grid solver, which is really by far the fastest, most efficient solver. Okay, right. And so there's some discussions here on how to set this up. Okay, and I will not really get into the details. The user's menu really explained this very carefully. So if I'll go back to this, so. Yeah, and so here, and this is page 12, really discussed about this multi-grid, okay? And so all the output actually would be the calculations, right, or for the highest resolution ones. And really, so that would be actually the topmost level of the grids, okay? And so, so that actually is kind of discussed here. And then, of course, then you have some, the radius, okay? So the inner radius, in this case, non-dimensional. Now it's about the Earth radius. So the inner radius for the core minor boundary is about 0.54, etc. Then the outer radius is the Earth, it's non-dimensionalized by the Earth radius. So therefore it's 1, okay, right? And then the next thing here will actually be really the so-called grids, the layers of. So this is where in the radial direction, you can actually, so if you want to refine your lithosphere or your up mantle, right, and you want to put more elements there, and this is, you can do that from here, okay? So you can, in the radial direction, you can divide your grids into different layers, then each layer can have different resolution in radial directions. So you just have to, really specify, for each of the radial grid layer, right? What is the starting radius, right? And what is the ending radius? Then what is the starting nodal number, right? So, and as I said, it's all being explained, okay, in this user's menu on how to kind of do that, to do the, basically we're talking about the grid refinement in the radial directions, okay, right? It can be done here, okay?
Is this,
yeah.
Sorry, thanks. I remember the work by Donna for Antarctica with the grid refinement. Is this the case that we have to, is this the part of the code that we have to change in order to obtain
that's a bit more complicated. So if you do the grid refinement in horizontal directions, like say you want to do that for Antarctic, right, or West Antarctic. You can certainly do that. Donna actually been doing that. I guess this code that when you download this now, you probably cannot do that yet. But if you're interested, we can certainly discuss. If you really need that, we actually can discuss how to do that. Maybe in some other time. Okay, right? Yeah. Okay. So now here there are some dimensional parameters like the radius of the Earth that we use to normalize the coordinates, right? There's the mantle density that we use to kind of normalize, and this is 40. We use a frame, so the density varies with the radius, right? But there is a reference density, and then there's a reference shear modulus, right? And then there's a density. So then the density above, and there's a density below. This would be the core density. Okay, and then there's this is the reference acceleration, then reference viscosity, and so this is 10 to 21 Pascal second. That's reference viscosity. So that we use to normalize all the viscosities. Okay, right. And there is also solver related information like this accuracy 10 to minus 2. This is really how. This is like when we solve the momentum equation, the matrix, in the matrix form, when we use multi-grid, right, iteration, then how much reduction we want residue to be, right? And so that's, so you can sort of set it up, like what we have here, okay? So this, yeah. So now then you have group 5. I kind of sort of said group 5, we almost never change that, okay? But they're kind of, the boundary conditioning, et cetera, right? And so, but anyway, so that actually is really kind of a description of the input file, okay?
Shiji, can I interrupt for a second? Sorry again. I'm still trying to understand your those reference viscosity, because the model, the prem file uses absolute Pascal values, so it's not scaled to 10 to the 21.
That's right.
So where is that reference value actually used?
So the reference, so we would read in that, say, VM5A from the file that is showed, right? And so those are actually in Pascal second, right? Like that column VM5A. So then once the code read in that file, read in the viscosity, and then actually we'll kind of divide or normalize those viscosity by this reference viscosity.
Okay, so it's all internal. So all the inputs are always in absolute units. This is just for internal scaling.
Right. So the code will normalize itself, and then of course all the actual calculations we use sort of normalized values or dimensionless viscosities. That's all the calculations are. And the actual output files, they're also mostly output in terms of non-dimensional numbers. So for example, the displacement is actually normalized by the radius of the Earth. So if we want to post-processing results to really say, right, to prepare a figure or to analyze our results like sea level change or the radial displacement, we have to kind of reading the output from the SVE calculations, then we rescale that back to dimensional numbers. So that's really that's what we yeah. So so any other questions? Okay, so that's pretty much really the key, right? Input files, so that's that input, right? That's really this input, 6G VM5A1, right? And so now if you, so I already discussed this, and so there are other input files, right? I just said like prem, that this one that we already discussed very quickly, right? That's here. You in this section, you actually see more detailed description of each of these files that got called in this input file, right? So, and so like this, here is the Earth model file, right? So it really explained everything. carefully. So there's that. And also for incompressible, and then of course, if you actually run incompressible model, your VP, the seismic, the P wave speed will have to be infinite, right? Literally, right? So this discuss how you would do it. And also if you have discontinued, if you have like viscosity, like VM5A, they got a viscosity step, right? And how you're going to implement that is all discussed here, right? And so then there's also, now this is talking about the viscosity, 3D viscosity, how you would actually prepare, right? This is the section 4.2.2. This is really for 3D viscosity, possibly 3D elastic structure, right? And this is really discussed, how you would prepare those files in the format that the code will recognize, okay, right? And so, and then this is actually now the section 4.3, and basically discuss the ice, essentially ice file, right? The temporal and spatial distribution of a load. And so the example we have here is I6G, right? And so, I think we already kind of mentioned about this stage file, and the details are discussed here, okay, right? You have a 122, one glacial cycle, 122, right? And so if you want around 2 glacial cycles, then you have to change this file, right? So that's all discussed here. And then there's just ice, then the I6G, right? We'll kind of chat a little bit about this already. And, it's really, you can sort of really see that. And so I'll just kind of give you a quick look. And so this would be, for the first stage, I6G, right? This is the ice model. So basically, you sort of see the 3 columns essentially, right? The first column is like the longitude, and this is a 1 degree by 1 degree, right? So 0.5, right, and 1.5, like 2.5 degrees. The second column is latitude, okay, and then the third column is ice height in meters, right? So this is essentially is what what we're talking about. This is ice, right? And so then for each ice file, and you have right, you have an ocean function file. This is essentially 0, 1, right? And for
You don't have an option to read NetCDF, because that would definitely, it would make
yeah, right now
grid options a lot easier.
yeah, I mean right now everything is done in a very, very simple way, that is you can actually see with your eyes.
Okay.
ASCII files. Yes,
Yeah.
those are, we hope in the future, all this, once we get over, so we sure everything's right, then yeah, we'll, into the binaries, yeah. So at the moment, there's no option for that.
So it's just this one fixed format. Okay.
Yeah, there are a lot of waste of disk space at the moment.
Yeah.
Yeah. So so let's see. There is I think this is actually, so by now pretty much I'm done with the input files. Okay. So there are the users menu. Let's discuss about the grids. And now the next section here actually for in the input in the users menu is on the output files. Okay. So so we have about 18 minutes before the end of this tutorial. Okay, so let's see. I like to give a talk, maybe 10 minutes, to describe this pre and also post processing, right? So what I actually want to do just quickly, for the next few minutes to really discuss the output files. Okay, so now the output files, I will just say there are basically 2 kind of output files. Okay, right. So they're all actually being stored in this directory, the bench bm underscore i6g, right? And that's we specified in the input file, right? And so I will actually just go into that directory, right? So we know this is actually all the files in this case will start with like case 1, because all the calculations are case 1, right? So there are 2 types of files. Let's say, of course, we're interested in surface information, right? Surface displacement, in vertical direction and surface displacement in horizontal east, east west, right, and sort of source north directions. So, so there's a file in that case. There's a file called topo surface, and now you have to realize that we actually have many CPUs, right? And in this case, we have about 49 CPUs that covers the top the top row of the blocks, right? And so that means if you actually output the final element results, then to describe, say, the surface information for present day or any given time, right? You have to have 49 files, right? Because you need, you have 49 cores that covers the whole surface. So that's essentially what we have here. So now, and so you have now I can sort of say here, if you just look at the case one top underscore s surface information, then this last number here tells you the time steps, okay? And so we have every 10 time steps for this surface information output, right? So then you have 10, 20, right? Then this number, the second to last, this number tells you the CPU numbers, okay? And I'll just kind of quickly, pick up a number. And so now this is essentially the number you actually will see. This is all for surface information, right? And so, this actually will give you things like you would imagine the gravity, right? The surface gravity, the surface displacement, horizontal, vertical, right? And so, and also incremental, the total. That's why you have so many columns. And this is being explained here, okay? And so this actually would be one type of information that is very useful, okay? And so a lot of the things related to observation, right, about the GI problems, the output, the raw output, they're all here in this file, okay, right? Now you can also imagine to do spherical harmonic expansion, right? You take the surface topography, and that from this, say, from this 49 CPUs, right, files, then you can imagine to take all that to do spherical harmonic expansion. That's actually what we have here. So that actually, for example, the TPS, spherical harmonic, and now if I say the 10th time step, right? So then this is essentially to take the surface topography from the GI calculations at this is 10th time step. Then we do a global spherical harmonic expansion. So you end up with a spherical harmonic, right? The L's, M's, and then the cosine terms, sine, right, for the spherical harmonic expansion. And then, then this all the way goes to degree and order 32, okay, right? And so so the output, there are really essentially there's two two type of output, one in terms, on the final element grids, and then the second is for harmonic expansion. Okay, so now, and then there, of course, there's if you're interested in viscosity, or if you're interested in stress in the mantle at different times, then we also have that output that's actually giving here in these files, like for example, stress, viscosity. So you sort of see, for example, I would have, let's say, this actually at the moment only output every 20 time step, right? And so now I'll just open up. This is again the last number is that 20 is a time step. Then the I guess the number before that is the number of CPU, the index for CPUs, right? So if you kind of open that, then you have basically, I think maybe the first column is viscosity, and the second column is it's your I think the second invariant of your stress tensor. Okay, right.
Shishi, do you have like post processing routines for combining all the
yes. And
X,
this
Y,
is why
'cause
I
that
want
would
to
be a
talk.
headache. Yeah. Okay.
Yeah, and that Toy is going to talk. Well, right. And so now that's essentially the output that I want, the file is actually really explained very carefully in this, right? Displacement, gravity, normally is all the output, right? And so really, so the user's menu kind of really explained that all very carefully, okay? And then this is related to spherical harmonics output. And so now, so that's it, right? So this is really output files. And as you can see, the fine element grids, they're irregular grids. They're not like a constant, degree, like a latitude, longitude, right? So it's not really that easy to visualize this, results. So this is where I think the, Tao actually will be able to help to kind of discuss very quickly about how to do the pre, and post processing. And I just want to quickly mention there is a cookbook example cases. Okay, there are just files we have here. There are quite some input files we have here, right? This is really for example cases. So there's another thing I really feel like important to mention that I bet most of you actually have analytic solutions for whatever problems you're doing, right? I think it's very, very important for you to really do some calculation using this CitcomSVE and then try to compare with the solutions from your own analytic solutions to see how they actually agree. Hopefully they will reproduce for 1D problems. Hopefully they will reproduce your results, right? And we did that. We used this analytic code from John Wall. And so all the benchmark we did really by comparing with John Wall's code. But I would highly, highly, urge you to do that, compare with your own analytic solutions to so you actually be sure that this code is doing, exactly the things you want. Okay, right? And that's really, really important. Okay, right? And so I think given that, let's see. I think that's all I have to say. Then so Tao, now you can take over. I'm going to stop sharing, and you can take over to say a little bit about this pre and post
Yeah.
processing. Okay. So,
Okay. Yeah.
Shiji, before you
yeah.
before
Yeah,
you
sorry.
to Tao, I have one question. Like in the input file, the group number 2. So when you're talking about this kind of loading, say the spherical harmonics, those kind of options, is always means the loading on the surface, or you can do the loading in the interior of the mantle.
So that for surface load, it's always a surface load, right? So it's on surface. But if you have a tidal loading, then the tidal loading will be everywhere, right? And throughout the core mantle boundary, in the mantle, if it's compressible, right? So yeah, I mean, so it really depends, right? But yeah, I guess at the moment the code cannot do internal loading like a mantle buoyancy loading. Well, it can do it, but it's not really, we did that in 2D, but not in the SVE 3D, yeah. Okay.
Thank you.
Yeah. So.
Okay. So can you see my screen here?
May I ask?
No, oh yeah.
Sorry.
Yes.
May I ask,
Okay.
Gigi, if you can paste the reference of the benchmark that you used to benchmark the models against, like the analytical solutions you said?
Yeah, that's John Wall's code. So that's an analytic code. Actually, the John Wall's code actually is already, one of the publications we had recently. Actually, kind of that his code is already, I'll type in the chat. We
Thanks.
actually can get that code from that paper. Yeah.
So okay. Perhaps I can start to. Oh, can you hear me?
Sure.
Yes.
Yeah.
Yeah.
Okay. Yeah, so I will start to describe how to using the post process and the kind of pre-process scripts that we provided. First I think we can first start from the post process since Shijie just described the output files. So we provide some general post-process code for processing the surface displacement and the relative sea level. One part of the code is to combine all the single CPU output file and to combine those files such that we have one file for the whole surface. And another kind of step is to interpolate those kind of results on CitcomSVE's irregular grid to the regular grid. And then we also have code for the sea level kind of calculation for user specified size. So you if you download the code from GitHub, you will see pre post processing tar file. After you unzip this file, you will see the pre post processing folder, and there are three directories in this folder. Let's first go to the post process directory. So in the post process, for the post process, most of the time you only need to modify one file called run or post p.sh. This is a bash script, so it will call other code in this folder. So in this run or post p.sh bash script, first we have several controlling parameters to determine which step you want to run. In the user's menu, we have detailed description about each step. Basically, the step two is kind of to combine all the single CPU output file to one file that contain for the whole surface. And the step three is do the interpolation from CitcomSVE's irregular grid to regular grid. And the step four is to do the sea level calculation. And for step two, we also have a multi-thread version, so so it can process multiple steps simultaneously. If you set one to each parameter, that means you want to run this step. Otherwise, you can set it to 0. And then we have some parameters to set so that you can specify which case you want to do the post process. Here I'm using the first parameter called SVE output prefix. Here I'm using the output from Shije's calculation. This is the case one that Shije just showed. So this is the prefix for the output. We can have a quick look here. So if I just because this folder has a lot of files, so it's hard to just rs out the files. I just show perhaps just the first the time step 10. So we have a lot of output in this folder. Once you specify this prefix, the second parameter is a file, right? You can name any. You can give it to any name, so it will just output some header information into this file. Then we have the start time step and end time steps. So which specify what time steps you want to do the post process. So in this case, 12:20 is the last time step of the of case one. Basically, it's the present day. And then you need to specify the number of CPU on the surface. In this case, is 48, and the number of CPU in the radial direction, in this case, is 2. And the number of node in X or in Y direction, they are the same in X, Y direction. This is the number of node for each CPU is 41. So it must be consistent with the case that you or the input file that you use to run this case. The detail, some of the detail is mentioned in the user's manual. Then some other parameters like what's the prefix you want to specify for the output files or the post-processed files. So you can name it to any name you want. Then this name will be used to create a directory for the post-processed file, and also used to generate the file prefix for the post-processed files. And for the multi-thread version, if you want to use the multi-thread version, you can also specify how many threads or how many CPUs you want to use simultaneously. Here is the resolution is the resolution of the regular grid that you want to interpolate it to. So here we set it to 1 degree. And the number of latitude and the number of longitude, it should be consistent with the resolution. If it's 1 degree, then the latitude is 181 because it's from the North Pole to South Pole with a step of 1 degree. And the longitude is 361. It's from 0 to 360 with a step of 1 degree. So those kind of specify the regular grid that you want to interpolate it to. Then the last three parameters you want to specify is for the sea level calculation. One thing you need to provide is a file that describe what the locations of the sites that you want to calculate the sea level. So here we have one example file called RSL sites group A dot position. So in this file, you can see it have in this example we provide 5 sites. So the first line of this file is the number of sites follows the first line. So we have 5 sites. The first column is the longitude, then latitude, then the site names. So you need to prepare this file and specify it here. Then the next parameter is just an intermediate file. If you it's described in the user's menu. Basically, it's similar to use static sea level, but it's not quite that. But maybe you are not really interested in this. The last parameter is the output file that contains the calculated sea level for the sites that you specified in this parameter. So I can do so the details of those parameters you can see you can go to the user's menu. We have a detailed description. So here I can just quickly show you. I can just you can go to the here. Well, now we are in the post process directory. You can just run use sh and run all post p. So it will process all the steps that you described in the input file. So we in the in this file, in the run all post p file, we said that we want to start from 1100 step and end at all the way to the 1220 steps. So we have this kind of maybe 20 steps. So okay, so basically now we finished all the 4 steps, including the combining all the single CPU output file to one big file for the whole surface, and also for the interpolation from CitcomSVE grid to the regular grid, and also for the sea level calculation. Now we can see here is the folder directory right for the output files or the post process files. We have, for example, we have the for example, the last file is called a map uplift. .1220 regular.xyz. So this is a text file for the cumulative uplift at present day. Yeah, so it's on regular grid. So the first column is the longitude and then latitude and then the cumulative uplift. But we also output the kind of net CDF file for the same kind of results. If you don't need it, you can just delete it. But it's just a net CDF file. If it may be easy to plot. So this is the kind of the displacement on surface. We can plot this displacement on surface using we provide a script, a simple script called plot grid data. This is here we plot the uplift rate at the present day using the netcdf file, and we use the GMT to do the plot. So you can, for example, sh plot grid data. So here we have GMT on our machine, and then it will generate this. This is the present day uplift rate map using I6G. So this, but of course, we also output the geoid, also the displacement in the horizontal directions. We also have the output. So here we also do the sea level post process for those sites. So here is the sea level file. So here is the output of the sea level for this case. So the first column is the time step, then the second column is years, then the sea level for each site. We also provide a simple script to plot this kind of sea level called plot RSL. So it's a very simple code just to show how to use those kind of output. So it's also using GMT to do the plotting. So here we run the sh plot RSL. So this is the output we just generated. So this is for I think it's for Churchill, but we only post process the last 12,000 years. So here is the sea level for the last 12,000 years. So this is the post process. We only provide those kind of several general purpose post-process code. Yeah, I guess I can also quickly go through the pre-process here. So
So Tom, maybe you can quickly just describe what does the pre-process would do.
yeah, sure. So the pre-process is the main purpose is to do the ocean function calculation. For example, sometimes you only have an ice model that describes how the ice distribution change with time, but maybe you don't have the ocean file. Then here the post process, the purpose is to calculate the ocean function. Ocean function is just a number. It is one if if the region is ocean, but if it would be zero if it is land or it is grounded ice. So here we in the GIA community, we usually do some kind of iteration to calculate the ocean function because the topography change with time. But here we only in this time we only describe how to do the initial iteration, how to do the first calculation given an ice model and how to calculate the ocean function using the ice model and a present day topography model. So that's the purpose of the pre-process initial, and to do the iteratively refine the ocean function, we need another kind of kind of layer of iteration rather than in the pre-processed refined ocean. This is kind of a little bit complicated, but we describe all the stuff in the user's manual and the benchmark paper. So here I just show you if you have an ice model, for example, I6G original. This is the I6G model from DigiParty A. This ice model covers the whole last glacial cycle from 122 to present day, but it does not have an ocean function supplied. So you can use the code called pre-calculate this code with an input file called input.preprocess. This basically will read in all the ice model file and also read in the topography file. Then it will calculate the sea level. It will calculate the ocean function through time. So if we just run this, it will quickly generate all the ocean function for each stage. So yeah, here is the generated files, both for the ice file and the ocean files. The reason we also output a new ice file is because we also calculate the floating ice and remove the floating ice from the ice model. We can have a quick look at so here is the pre-processed ice file. It has this kind of format like Shijie just mentioned, and also the ocean file. It has a similar format. So I guess that's the basic of how to using those pre-process and post-process. Is there any question? I guess I just quickly go through, but the details are you can find in the user's manual.
The Appendix B, yeah.
Yeah.
Can I ask a question about refining the ocean function?
Yeah.
So you run this initial version, and then you presumably run Sitcom and have some that's deforming through time. And so I'm wondering, is there then some iterative process where you then get a new ocean function based on that new topography and then put in those new ocean loads?
Right. That's the purpose of pre-process refine ocean. Basically, you take the results of one CitcomSVE calculation and for example the topography, and then refine the ocean function using the code provided here.
And then do you have to rerun Sitcom with those new ocean?
Yeah, sure. Once you got a new ocean function or new ocean history, you need to rerun the CitcomSVE. That's the iteration that we need to do.
Right.
Okay. And do you check that converges, or like is there a typical number of times that you go back and forth and then call it good?
Oh, for the convergence, we checked with the analytic code. So yeah, the convergence is similar, just similar to the Kindle 2005 paper. But for the CitcomSVE calculation, it should be the same because it's kind of we did the benchmark for the 1D, so the CitcomSVE calculation it has no problem. So for the sea level iteration, it should also do the job.
Yeah, you probably need like 2 to 3 iterations, right?
Yeah.
Big loop iteration, 2 to 3, that will actually converge, reasonably well.
Yeah.
Okay, that makes sense. Thank you.
Yeah. So for the sea level calculations, this iterative sea level calculations, I think TOS benchmark paper 2025 I think we actually compare with the solutions given by Glenn, and they really agree with we agree with Glenn's results very nicely.